Okay, next we have a definition, and this definition states that a sequence of the set A subscript n is bounded above if there is a number m such that A subscript n is less than or equal to m for all n being greater than or equal to 1. It is bounded below if there is a number lowercase m such that lowercase m is less than or equal to the sequence A subscript n for all n being greater than or equal to 1. Now, if it is bounded above and below, then we would say that this sequence is a bounded sequence. So, for instance, the sequence A subscript n, which is equal to n, is bounded below where A subscript n is greater than 0 but not above. The sequence A subscript n, which is equal to n divided by the quantity n plus 1, is bounded because A subscript n is in between 0 and 1 for all n. Now we know that not every bounded sequence is convergent. And then, for instance, the sequence where we had A subscript n, which is equal to negative 1 to the power of n, satisfies the fact that the sequence is in between negative 1 and 1 inclusive, but it is divergent from example 6. And not every monotonic sequence is convergent, as A subscript n, which is equal to n, approaches infinity. But if a sequence is both bounded and monotonic, then it must be convergent. And this fact is stated without proof as Theorem 8, but intuitively you can understand why it is true by looking at figure 10. So what it's saying here is that if this sequence, A subscript n, is increasing, and A subscript n is less than or equal to the value of m for all n, then the terms are forced to crowd together and approach some number L. So for Theorem 8, the monotonic sequence theorem, every bounded monotonic sequence is convergent.